Welcome, everyone. My name is Krista Mulherin, and welcome to the next webinar in GoProto's Office Hours series. Today, we are going to be talking about materials for plastic 3D printing. What are the options? So a couple of housekeeping items. Notice that your questions are going to be listed on the slides throughout, but also feel free to ask questions as we go in the Q&A box. Then we'll also, at the end, we'll have additional time for questions, hopefully. So let's get started. So first off, I want to introduce Jesse Lee. He's the president and CEO of GoProto. Jesse's a 25-year student of the rapid manufacturing space. He's been a part of incredibly diverse product development programs, from early prototyping for products like the iMac in the 90s through high volume additive manufacturing for projects like HP's 5i80 color printers. Listening to client partner needs, utilizing the latest and greatest array of manufacturing technologies, and working with the best people in the product development and manufacturing community is what Jesse finds most exciting. Welcome, Jesse.
Thank you very much, Kristen. Appreciate it. Can you hear me okay, first off?
Yep.
A little sound check. Great. Excellent. Okay, so then just a little more. This is going to be an hour-long discussion. The intent here was, as you all registered, we asked you questions. We looked at those questions and essentially built the webinar around that. So the intention is really to discuss what it was that you were looking for in information. We'll talk a little bit to start with about GoProto and why we are, I guess, experts in the field and why you should listen to us, and then we'll go through and talk about each of the materials. For the first half, we'll talk in general about the materials, and then the latter half we'll talk about the new material that we've introduced, which is a 3D elastoprint elastomer in the multi-jet fusion process. So excited to go through it with you all today. Again, as Kristen said, if you have any questions throughout the webinar, please type them up in the chat. We'll take a look at them and answer them as we go along. Some of them may be answered later, so we may integrate them or have them know that they're going to be answered and have them as part of the presentation. So with that, we'll get started.
Great. So here is the topics we'll be covering today. We'll do a very, very brief introduction on who is GoProto. Then we'll do an introduction to the different 3D printing technologies for plastics in 3D printing, the material options within for those different technologies and how they compare, and then the material properties such as tensile strength, elongation, impact strength, and we're going to show you a graphic on how those all compare as well. And then, as Jesse mentioned, we're going to wrap up with a discussion on the newly released 3D elastoprint for the TPA elastomer. And again, feel free to answer questions as we go along. To get started, Jesse's going to do a brief introduction on GoProto.
Yes. So this little graphic is just designed to show that we do prototype through production plastic and metal parts. So the tagline up at the top: quick turn, on-demand, custom manufacturing. So we offer everything from upfront concept models that are just essentially ideation models for you to show your stakeholders. So they're often 3D printed or machined models that are painted, textured, put graphics on them, make them look like the real thing, so that you can show them at trade shows, or I guess virtual events now. More so, and then to your stakeholders, photo shoots, that sort of thing. So we understand the idea of cosmetics and graphics and fitting parts together early on in concepts. So we're not expecting you all to come to us with always, just exactly dialed engineering files. A lot of times it's a work in process, and we understand that. So this slide kind of shows we do the full gamut. So concept models, 3D printing is a big part of what we're here to talk about today, and that is primarily 3D printing in plastics and metals we do. Today the discussion is mostly on 3D printing in plastics and also elastomers as part of that. But we focus on 3D printing for the stage of ideation through prototyping. So we discern that between, near the bottom you've got additive manufacturing, just 3D printing, and lots of them with a quality control program and an inspection plan and so on, designed for manufacturability analysis to dial in for lowest price and fastest throughput and so on, to be able to deal with higher volume. So then back up, urethane castings is something that's important to know that we do, because it's a bit of a slowly dying art. It is generally used for cosmetic parts, often larger parts. It's been used a lot for elastomers, which again, we're going to talk about the 3D Elastoprint. Urethane has been kind of our main compromise when it comes to, or our main way to get a compromised material for elastomers in the early phases of ideation and prototyping. So that's still something we do very well. Casting color and texture, clear parts, tinted, that sort of thing. We are really, really good in that space as well. And then CNC machining, that's, as you all know, machining of parts from billet in plastic and metal. We do all of the available materials that are available. That's a very important thing to know. We know how to do, because again, as we're looking at, say, 3D printing versus machining, what are the options? To know that we have all of them is important, because we can really objectively look at what is it that you are trying to do and then recommend the right process. Sometimes there isn't a clear-cut winner. We want to present both, talk to you about the pros and cons, and then you can make an educated decision on what's going to work best for your program. Then tooling and molding, that means injection mold tooling and molded parts. Again, we've focused on this. This is a technology we've done for 20 to 25 years. Our company is new, but myself and most of the project managers at our company and sales folks have been in this industry for a long time. Knowing that we do tooling and molding, we've got the whole upfront design for manufacturability analysis, the quality plan, the progress reports and updates on how we're doing on the project, and then molding, inspection, all of that thing, that whole mentality that is built into manufacturing, we are able to apply to 3D printing to get to additive manufacturing. So we are, rather than just say buying some printers and getting started with 3D printing, we've added additive manufacturing or 3D printing as a tool to help us bridge the gap, deal with things like supply chain uncertainty and things like that are happening with COVID. There's a lot of things that we can do with additive manufacturing because we're able to use our expertise for injection molding and the whole quality plan around it and apply it to 3D printing to make a truly production capable additive manufacturing program. Then there's two last things there. Sheet metal, important to know, again, we do prototype through production sheet metal. So often in a bill of materials, you've got metal components that are, say, chassis or flex or any of the electronic components, things like that. We do sheet metal in low to high volume in steel and aluminum and copper and other materials that are needed. So that's important to know. And then additive manufacturing, I kind of talked about already. And then importantly, finishing. And we'll talk a little bit about that today, finishing to apply graphics, colors, textures, all those sorts of things. Important to know that we can put on the final touch to make your parts usable. Okay, so that's a little bit about kind of our spectrum of processes. And again, important to know the one-stop shop idea means that we can, we are truly technology agnostic. GoProto is a privately owned company. We're not part of one of the 3D printing machine manufacturers. So, we really have all the available tools in the toolbox, talk to you about what it is that you're looking for, and then make the right recommendation. So the next slide. So today we are talking about primarily the technologies that are listed here. What 3D printing technologies are we talking about? Land of acronyms. Let's go through these. We're talking about MJF, which is multi-jet fusion. It's a powder bed technology. So the material itself that the part will be made from starts as powder, and then a detailing and fusing agents are applied to the surface of the material in the cross-sectional shape of the part, and then a high energy light is passed over it, and wherever the droplets have been applied, the powdered nylon will sinter together, and then a roller comes across and spreads out a new layer, and the process is repeated over and over. So powder bed technology, there are no supports in that technology. It's important to note. The parts are self-supporting because the powder that surrounds the part isn't sintered, so it ends up holding it nicely. So that's important to know, because we'll talk about material properties and things that come up as a result of whether a technology has supports or not. Then the next one is FDM, or fused deposition modeling. This is extrusion based. This is the most ubiquitous. Most people have these in colleges. It's kind of the maker type machines, a lot of them. There's kind of that maker space type of machine, and then there's the commercial machines. And we run, of course, the commercial machines primarily. So the Stratasys, we've got the F900s and the 450s. FDM has been around for a long time. It makes some basically it's used a lot, and we'll go through this in the slides later, but it's used mostly for its ability to make production grade parts in materials other than nylon. Multi-jet fusion makes parts primarily nylon based. Then SLA, or stereolithography, is a laser-based photopolymer process where it's a liquid photopolymer. Laser hits the surface of the photopolymer, and we've got a phase change that results. So that when the laser, wherever it hits, it cures the material, turns it from a liquid into a mostly solid. Layer by layer, supports are added to the part, attach it to the build platen, and then the part builds up layer by layer, and then when it's done, we take it and break it off that build support, take it and put it in a ultraviolet finishing oven, essentially, to finish the curing process, remove all the supports, clean the parts up. SLA is, we'll go through the pluses and minuses. Primarily, it's best for high precision and also clear and white parts. So it's still got some very good applications. It is one of the older technologies here. SLA, FDM, and SLS are all kind of on the older end. DLP and MJF are much newer. So then DLP, digital light processing, you probably know this mostly by the brand name of Carbon. That process is exciting because it's fast. It is similar to SLA. You kind of notice it's actually pretty similar. It's just that it's upside down and has some different technology, but essentially it takes a photopolymer that's liquid and through some exposure to light, turns it into a solid. So it's quite fast. And then SLS, selective laser sintering, is another powder-based technology similar to multi-jet fusion, but you'll notice with a little graphic there, instead of a powdered material, instead of a droplet process where the fusing and detailing agents and then high energy light passes over like multi-jet fusion, SLS is laser based. So wherever the laser hits the material, it fuses the material together, it sinters it together to form the part. So we're primarily focusing on MJF, FDM, and SLA. Those we do at our facility, brick and mortar facility we have in San Diego. We do offer DLP and SLS, but not in-house directly because the other technologies generally fill in quite nicely. There are just a few where DLP and SLS can do some things that the others can't. So of course we still offer it, but the others we do in-house. So we're focusing on those primarily today. All right, Kristen, let's go to that next slide. Yes. So a lot of you asked that over on the right here in our slides, we've got, these are questions that are from you. So hopefully you'll start to see maybe even some of your own questions here. But we'll talk about the subject matter on the left. I'll also look at then the questions on the right, so we can talk through them. Multi-jet fusion, FDM, and SLA are what we're talking about here. And you all asked, like, what are they best for, and also what are they not the best for? You know, we're not always going to say, hey, this process is awesome at everything, because none of these are. They've all got some pros and cons and some things to look out for. And hopefully in understanding those well, like any good toolbox, you'll understand when to use each tool. You know that you can always come to us and talk to us about what the options are, and we'll make recommendations so that you do have the most education about it, can make the best decisions, so you end up having the best experience. You get parts for the fastest, the least expensive. Your stakeholders, your managers, your investors, or whomever are going to be the happiest because you use the tools the best. Your product development is fastest. So what are they best for? Let's talk about them fairly quickly here. Multi-jet fusion is great for durable, and isotropic production nylon parts. So a key word I want to talk about there real quickly is isotropic versus non-isotropic. That just means that the part is similar properties in all directions. You've got the X and Y, which is on the build platen plane, and then you've got the Z, which is the height of the part. And the great thing about multi-jet fusion that is different than FDM and to some degree SLA and certainly SLS and DLP, as we showed on the last one, is that it's the most it's the most isotropic, meaning that the properties are the most similar all the way around, which makes it quite usable for lots of production applications. So that's something to keep in mind there. Next thing down, low to high quantity produced quickly. So multi-jet fusion has the ability to scale faster than really any of the other technologies that we have here, which is one of the reasons we have invested in this technology heavily, because we think it's got some fundamental architecture advantages over the other technologies that are going to allow us to scale it. We are a very close partner with HP that makes the multi-jet fusion machines. We're a digital manufacturing network partner. We have 8 of them. We have 6 of the 4210 machines and 2 of the 5210s. They're new generation machines. So that allows us to produce a few parts quickly for you. So just the kind of prototype use, as we showed in that graph earlier, kind of prototype through bridge. And then if you wanted to get into high quantity, we have the volume to be able to make a lot of parts quickly. So that's really an important thing. This technology can scale, which is different than the others. okay cosmetics. I want to point that out. I am going to be showing some parts from time to time, and from what I understand, I don't see the screen the same as you all do, but we've got the PowerPoint, and then my little window is kind of small, so I'll hold up some parts from time to time to be able to show them. That'll be kind of mostly, I think, later. Kristen, is that how we're going to do that? But I'll just kind of show some parts to just show cosmetics. Hold one up here. Cosmetics are quite nice. This is a smooth part, but you see it's a gray color. Looks nice, but it's best used for things that are not going to be what I would call Class A surface finish type of parts. They can be used for that, but that requires quite a bit of secondary operation, which means your part cost is going to be kind of higher. So if you're looking at like, where do I apply this type of technology? Okay cosmetics, generally black or darker color. If you get into the lighter colors, white or yellows, you're going to need to paint them or do some other graphic work to make them those colors. So then not the best. This technology is thermal. Things heat up and cool down. And so large flat parts don't work all that great because they tend to warp a bit. So just something right there, not the best for large flat parts. Super small, super high precision where parts are going to be fitting together. That's not a huge strength of multi-jet fusion. Multi-jet fusion can make fantastic small feature parts, but they tend to be, if you just need them small, like I've got a little sample here. That's a comb kind of feature that has some lattice, some tiny features on here that it can resolve very well. But the tolerance of these, if you were really getting into nitty gritty of tolerance, these things fitting together, you'd find that it varies a little bit here, but it can make these kind of tiny features. So just keep in mind the difference between a small feature that will work for your assembly versus something that actually has to fit really tightly together. It might be a little bit of a struggle. Okay, so then back to the next ones. Thank you, Chris. And hopefully you all can see we're kind of toggling a little bit. If there's any issues, please essentially raise your hand in the chat and let us know. So then I say Class A or cosmetic or chromed parts. That we can do that. We understand it. We know how to. It just takes a lot of work, which means it's expensive and takes a little while. FDM, let's talk about that. FDM, as I mentioned earlier, is used primarily because you want to get parts in materials that are like your production parts. Someone asked what materials are available, what's the most like ABS? And the answer is ABS and FDM. It's the same material. It's just made in an extrusion spool and fed through the machine, and out comes an ABS part. So we have ABS, polycarbonate, PC ABS or polycarbonate ABS blend. There's ASA, which is great for use for environmental. It's great for if you have things that are going to be exposed to UV and so on. It's great. Ultem, there's two different grades we primarily use. There's a flame-rated, flight-ready material, Ultem 9085, and then 1010 that tends to be used more on medical type of parts, things that are going to be autoclaved, things like that. Ultem is a fantastic material, high temperature, capable material. And then I mentioned flame rated and flight parts. So back on Ultem, we've also got a flame rated ABS. So that's primarily where FDM is used. Also big parts. I mentioned we have the F900 from Stratasys, and that's often used in transportation. That's used in large medical panels, things like that. Tend to be used on the larger machines. By that I mean a couple of feet cubed. So then it's good for fairly small to quite large parts. I just mentioned the large. It also can do pretty small. So it's got a good range of size capabilities. So that's important to know. I'll note later that it's not great for tiny parts. So that's down further. Lower tolerance parts where rougher surface finish is okay. By lower, I mean not quite as precise, worse tolerance. FDM is not known for extraordinarily tight tolerances. We can do some very good tolerances in X and Y, but when you enter in the Z, stack build layer built upon build layer, you start to kind of lose some of that advantage. So that's just something to keep in mind. This process FDM has one of the properties of the material, the properties of the part are most affected by build orientation in FDM, more so than with MJF or even SLA. So then not the best for high precision parts, parts where non-isotropic properties are required. So that means kind of like picture plywood. FDM is a lot like plywood, where it's really strong in one direction, but you flip it the other and it's not strong, not very strong at all. So the reason for that is because the build layers of the part can actually pop apart. If you've got a thin-walled part, part, you expose it to maybe some impact or some heat, you can actually get the build layers to sometimes kind of delaminate, or if you're going to be cutting it or machining it, you can see that parts might break. Also, if you picture a part, let's say a housing that's got clips or bosses on the inside, most of the part is built in the XY direction, but clips might be built in the Z. Those clips can sometimes be quite weak. So it's not that you're really breaking the material, it's that you're breaking the build layers between each build layer. You're delaminating essentially. So that's something to keep in mind. Orientation is critical. And then also high cosmetics. So FDM builds parts, you've probably all seen a lot of them. It builds parts with quite visible build layers. Surface finish can be rough. It's also, someone asked about hermetically sealed. It will tend to leak material. It can leak air because they're not completely bonded from layer to layer. And as it goes around corners or radii, the step overs will create some air pockets. And so you end up with non-cosmetic sometimes, and also some issues with air and liquid going through. So then quickly, so that we can stay on pace here, SLA, stereolithography. We still use this technology. It's been around since, this is one of the first 3D printing technologies, been around since the early 90s. It is still great for high resolution with smooth surface finish. Lots of you ask, like, what can I get that's got the best surface finish? And that is, SLA is what we would generally recommend. It makes, I've got sample parts again. It makes parts with, I'll hold it up, try to hold up the camera here. If you can see, it's got really nice, little details, great surface finish. This is white. This is built in Acura 25 material at our facility in San Diego. You can just see that it's got nice, clean surface finish. Nice little details along here. So that's when we tend to use it, is if someone wants, nice surface finish and the ability to, say, sand and paint. If you've got two housings that need to fit together extremely well, SLA is a great fit for that. So check fit or tight fitting components. And then if you've got parts that are going to have high cosmetics with the need to paint, so you want to sand, paint, make them look like a model bag. I mentioned that we do cosmetic models. This is the technology we would tend to use before MJF or FDM. It's not the best for, because it's a photopolymer that's simulating ABS or PCABS, or in the case of clear parts, it's simulating, my tiny little window, you can say I'm holding up a clear, simulating polycarbonate or ABS, acrylic. It's a great for those, but it's not very strong. If I take this part, I could break it fairly easily. This is the one I'm holding up here, clear part. I could break it fairly easily. So it's great for check fits and kind of those early prototypes, but it's not going to stand up to thermal load. It's not going to stand up to repeated flexing all that well. If you've got clips on it, they'll snap together, but they also might snap apart fairly soon. This also is a photopolymer that changes state when it's exposed to that initial UV light. We then cure it afterward in a finishing curing oven, but the curing doesn't stop when it's done. So if I'm in an office here with ultraviolet or with fluorescent lights, if this sits out on my desk or sits in the windowsill and is exposed to sun at all, it will continue to cure, and this part will turn kind of suntan. It'll turn sort of amber colored, and it gets more brittle. So the mechanical properties that are here, what we're here to talk about a bit today, will continue to degrade over time. So consider that when you're talking about either stereolithography or the DLP technology. Both of them tend to continue to kind of age as they go along. All right. So then high strength is an issue with SLA. High or low heat, it's not great with heat. None of the materials that are out there are going to come close to FDM or MJF. Even though they've improved, they're better. We've got some great stuff in SLA. It's still not as good. It's still a photopolymer. And then high quantities, it's not great for making, so you make 5-10 prototypes, maybe some parts to kind of get you through bridge, but you want to make 5,000 of them. SLA is going to tend to be pretty expensive. We don't get a lot of economy of scale like we do with MJF, sometimes either FDM or SLS. So something to consider there. Then quickly, how do they compare? I just kind of want to go through those, make sure I've answered them. What can you not print? We talked about that a bit. Resolution is something, Multi-Jet Fusion's got some good resolution, better than FDM, not as good as SLA. But because MJF is a technology that does not have supports, you can build features like the little comb that I showed earlier that are tiny, and know that you don't have to break supports off and figure out how to not break the part. So the resolution isn't quite as good on MJF, but its ability to be finished without breaking them actually sometimes means you can make smaller, finer parts on MJF. So a little counterintuitive. We can coach you through it. Surface finish, we talked about that. Production versus prototyping, that kind of goes from left to right here. Multi-jet fusion is definitely best for production. FDM can be used for production. If you've got some lower volume SLA, we generally wouldn't recommend it. There is also SLS that can be used for some production, though it's a little slower and usually more expensive in high volume than MJF. What is best for thin walls? Talked about that. MJF is great for thin walls. Sometimes, though, it can have warp. SLA is definitely going to be better at producing thin walls. FDM is not ideal for real thin wall parts. And chemical resistance, we did talk about that with Ultem. FDM makes parts in production materials. So does MJF. MJF is producing parts in production nylon-based materials, also polypropylene, and so it can reduce chemical or resist chemicals very, very well. So okay, that's kind of a rundown of those three. Kristen, you want to go to the next slide? Just a little time check. We're about halfway through. So pretty soon we want to be talking about the Elastoprint. So let's talk about FDM quickly. What do we have here on materials? On the left shows nylon. Actually, the main topic there should show nylon, and then Ultem 1010 9085, and sorry about that typo, and then ABS PC on the lower left. So this process is great for producing parts in production grade plastics. So if you know that you're going to be exposing it to certain chemicals that it needs to resist, you know you have a certain heat deflection temperature you're looking for, this may be the best route to go. So which materials, one of the questions I mentioned earlier, which materials are most ABS-like? Actual ABS produced in FDM would be the answer there. This is another question. Are there any options for compostable printing? One of you asked. And none of these actually compost, but one of the materials here, PLA, we can make is actually, that's not listed here. We run it on one of our other printers. That is, I think that's polylytic acid, and that is produced from plant-based material. So it may not compost when it's done, but it at least comes from a non-petrochemical origin. Its composition is not petrochemical. And then yes, autoclavable. We can definitely autoclaving, I think, ranges somewhere between 150 to 100 or 210 or so Celsius, depending on what type of autoclaving you're doing. And several of the materials in FDM could be autoclaved, which are suitable for high temperature. We've got all the programs for running all of the materials in FDM in the Stratasys machine. So down the lower right, there's an Antero picture, which is PEK, P-E-K-K, polyethyl ketone. It's most similar to PEEK, and it can, it resists just about everything. It's really an amazing bulletproof material. It's really, well, it's not actually bulletproof. I should be careful there, but it's a very, very strong material. So is Ultem. We've got chopped carbon fiber, makes beautiful, strong parts. So there's a lot of strength characteristics you can get out of FDM. UL flammability rating, that is the Ultem 9085 material is a flight rated, flame rated. I think it's V0 is the flame rating. So that, and then also the Antero. Antero was just certified by Boeing to be flight compatible. So this is, if you're just looking for just that property, then that's what FDM would be great for. And are any of these materials medical grade? The Ultem 1010 is medical grade. All right, let's go to that next slide, Kristen. Stereolithography. We talked about this. Just going to go through there quickly. Some example pictures of clear parts. FDM still, or excuse me, SLA is still a great fit for clear parts. If you're doing light pipes, lenses, windows, housings that you just want to see interferences behind to make sure that your cables and your printed circuit board and your sheet metal are not interfering, clear SLA is still the way to go, and we do great SLA work. And then white is another advantage of this versus multi-jet fusion, which generally produces gray or black parts. And then we've got the range of Acura materials from 3D Systems, the 25, the Extreme White 200, and 60 clear, which is the part that's pictured there. And then we also run Somos 11 122 clear, and then Nex. Somos Nex is a great material, white. So are there any materials that are optically clear? Yeah, we talked about that. That's important to know. You can see through it. It will pass light, but if you're actually looking for actual optical performance, we would recommend machining acrylic or polycarbonate, because that actually will test optically clear, whereas SLA won't quite. What materials provide the highest resolution and surface finish? These ones that we have listed. SLA is great for resolution surface finish. All right, Kristen, let's go to the next slide. Perfect. So let's talk about multi-jet fusion here a bit. Multi-jet fusion, again, is the technology introduced by HP about 4 years ago. We've been involved in it since the very beginning. We were one of the first companies to buy the printers in the US. We bought 6 of them, the 4200s, and then just recently we've added the 5210s. So our capacity is one of the largest in the country. We run all the various materials that are available, and we've got very high expertise in how to run it well, so that you end up getting good parts. So the materials we run are generally nylon based. We do also have polypropylene, but looking at the nylon, this is kind of the workhorse, the PA12. That's the part pictured in the upper right and also the lower left, and the one in the middle that says GoPro, that stops right there. That's nylon 12. It's kind of the workhorse, great material, good general purpose, builds decent quality resolution type parts, can be dyed black. It really runs quite nicely. It's what we run most of our parts in. Glass bead filled is it actually, surprisingly, something to note here, glass bead, the purpose of this material is essentially stiffness. If you have something that's going to take essentially a static load, you don't want creep, the glass bead filled PA12 is the one for you. It is glass bead, not glass fiber filled. That's because the powder for HP has got to be round shaped, and it's tiny. So you end up with these tiny glass beads, and that can actually reduce the part stiffness, or excuse me, the part strength and its impact resistance. So, and also its heat deflection is actually slightly lower than unfilled PA12. So kind of counterintuitive. Then PA11 is important to note. PA11 is castor bean oil based. So back, we had a question on anything compostable. While it's not compostable, it comes again from a non-petrochemical origin. So you can eat all the materials that PA11 has. That's pictured in the lower right. PA11 actually also prints a little bit better than PA12. It doesn't have, there's a cupping thing that happens with PA12, and that doesn't happen as much with PA11. It's also highly flexible. So you can make parts, if you can see my little window again, you can make very complex shaped parts that flex quite amazingly in PA11. So it's something to consider if you have an articulating arm. I've got a little part here that is a zip tie, so you can take it. This is rigid, but then it has the ability to flex. So if you're making anything that is, say, cable management or fasteners, you have something that's going to really need to flex. I showed earlier, this part is actually something that goes over the leg. So pretend my arm is a leg, it's body armor. It can take impact that's higher than the PA12. All right, so Kristen, back to the other slide. Thanks for toggling. Then polypropylene, that is an important material to know. That's fairly new. That material takes impact well. It is flexible. It's great for doing welding. It's obviously used in automotive a lot, so we brought in polypropylene. And then excitingly, elastomers is something that has come up. The part that's pictured in the upper left, and also the middle one that is flexing, is TPA, or thermoplastic amide. So that material is amide based, polyamide based, just like PA12, but it has a polyether block on the molecule that makes it flexible. So anything that's kind of the nylon 12 can, say, resist temperature, chemical, all this sort of thing. The TPA is quite similar, just has the flexibility, bringing it down to 90 short A. And then TPU we also offer. There's one from BASF and one from Lubrizol, and those are slightly harder than the TPA. They do have some applications as well, though. So then quickly going through, is MJF production capable? Sorry, Kristen, yep, just looking at these. Yes, it's production capable, compostable, we talked about. Material gives the best isotropic properties. That this process definitely does. What is the best material process for thin snap features? And this is, multi-jet fusion works great for small, thin snap features because they will live through the flexing. They'll live through, snapping together. So that's the answer to that one. All right, next. How do properties such as tensile strength, stiffness, elongation, and impact compare? So this next slide, we wanted to show you, I'm not going to talk through this too much because it's really, there's just so much data here, but looking at tensile strength, stiffness, elongation, impact strength, you tend to kind of see some inverse relationships. The parts that are the most flexible have the highest elongation, so the third one over are going to also have the lowest tensile strength and stiffness, of course. Impact strength kind of depends. It doesn't really relate to the TPUs as much, or TPA. But you see that we are aware of all this so that we can take a look at it. If you are looking for something with really high tensile strength, we of course have got the materials to run for you. If you're looking for something with really high elongation, you want something elastomeric, we've of course got that material for you as well. So just kind of know that we can run through this with you, talk about what you're looking for, and then we can make recommendations for you and quote them in the best parts. I'll kind of pause here real quick before we get into finishing processes. Kristen, have any other questions popped up that we should address?
Actually, yeah, there was a question on related to tensile strength. What's the comparative percent yield or ultimate tensile strength of MJF nylon parts versus injection molded nylon parts?
Oh, great question. So that's something that's pretty exciting in that multi-jet fusion. You see that the tensile strength is there. The multi-jet fusion is the blue one. So you see that PA11, as I mentioned earlier, is higher. Nylon, the PA12 is kind of about in the middle. The black ones are the FDM materials here. And so, nylon PA12 is about in the middle of the available materials. If you compare that to an injection molded PA12, it's going to be pretty similar, definitely less, especially in the, it is quite isotropic, but it will perform a little bit less in the Z. So its impact, or tensile strength rather, will be a little less in the Z. But compared to injection molding, it's closer than any of the other materials are compared, or processes compared to their injection molded counterparts. So if you say made an ABS part in FDM and then compared that to an injection molded ABS part, it would be less similar than if you say made a part in nylon 12 in MJF and then injection molded it in PA12 and compared them. Those are going to be much more similar. So that means you can use 3D printing in MJF for production for parts that you would otherwise consider injection molding. And it's going to be a little less. Also, something to consider that we talked about that we'll talk about here on the next slide. Let's go to that next slide to kind of partially answer that, Kristen, is finishing processes. We wanted to talk, or what I'm starting to allude to here is the center one, the vapor surface smoothing. So we have a machine in San Diego that is from AMT. It's a post-processing. It's called the Post Pro 3D, and it's a vapor polishing process. So it exposes the surface of the parts to solvent, and then that's in vapor. It reorders the molecules and then resets them, essentially making them look smoother. It also kind of locks them together a little bit better than before they were smooth, and so you end up with higher impact strength, higher tensile strength, makes them a little bit more production capable in terms of, say, impact strength or tensile strength, because those molecules are locked together a little better on the surface. They go down to about 0.4 of a millimeter, so it can have a significant impact on sorry for the word there, but a significant impact on how well the parts resist impact. Okay, so we need to kind of move on. So looking at finishing process, are all MJF parts black or gray? So that's those are pictured. The center part there is gray on the left, and then we can dye those parts to be black, or in the upper left we can also do dark blue, dark green, dark red, basically dark colors in dyeing. We do that in-house, works great, it's inexpensive, it's fast. Then to lock the dye in, we can do the vapor smoothing, and that also makes the surface finishes a little bit nicer in some ways. It can also show some imperfections, so it's like any tool, you got to kind of know how to use it. But we can get different colors there. Also, of course, we can paint, and we can do what's called Cerakote. That's something you can look at cerakote.com and learn more about that. This is a paint. It's basically like a paint application, then post-baked, and the material is ceramic based, so it resists a lot of chemicals, high heat, wear, because it's ceramic. So it's a great process for finishing parts that need to be more durable. That also, between smoothing and Cerakoting, the second question down, are any materials capable of producing parts that are hermetically sealed? Something important to know, that smoothing and Cerakoting, or smoothing and sometimes painting, can help seal the surfaces so that you can expose the parts to pressurized air, pressurized liquid, and they will seal. That is mostly for multi-jet fusion. FDM, sometimes the holes are big enough that kind of nothing will really fill them all that well. SLA won't generally take the temperature or pressure, so that's not really a factor here. We can also smooth and Cerakote. Actually, I don't know, we haven't really Cerakoted the SLS, but we have smoothed it, so it can help there. And then DLP won't react to those either. Hydrographics, we do applying graphics to generally multi-jet fusion parts, and that can take, that can alter the outcome to some of these questions too. If we apply Cerakote or paint or hydrographics and smoothing, then the cosmetics and the mechanical properties will change. All right, then
Quick question for you,
metallization.
Jesse, on the vapor smoothing.
Yes, of course.
Does the vapor smoothing affect dimensions or warp the materials?
Answer to both is yes, slightly. It kind of depends. First question is on the dimensions. It's about a 0.4% is what we quote that it will affect the dimensions. It's surprisingly small. It doesn't affect the dimensions all that much because it's not, a lot of times when you think of smoothing or something like that, you're thinking of kind of melting, and it doesn't melt the material. It essentially reorders the surface molecules, so the material doesn't go away like it does with some melting processes. So a little bit is the answer there. And then on warping, sometimes it can. If you've got a thin part, because you're reordering the surface molecules, if you have, and it goes down about 0.4 of a millimeter, as I said, if you have a wall that's 1 millimeter and you're smoothing the part, and 0.4, that's 0.8, are essentially kind of being reordered, then you've only got 0.2 of a millimeter to kind of hold the whole thing together. And so sometimes thin walls can warp a bit if you smooth them. So thicker, they generally don't warp. It's not temperature based either, so it doesn't say relieve any thermal stresses that are built into the part. So it can affect warping sometimes. That answers that question. If you need any more, then we can pop in later. And then metallization we do as well. So let's move on to the next slide, Kristen. Okay, great. So we've got about 25 minutes or so. We'll talk about the next 15 minutes. We wanted to talk through the 3D Elastoprint. We're excited about this because this is a new material, new to the market. We have been involved very, very closely with the manufacturer of the material. It is Evonik and HP. We've gone through alpha and beta. We've been working on this material for a little over a year. We've been involved in as I said, the alpha and beta testing phases, and we just introduced this material live to the market at the end of October. So this group is one of the earliest to hear about this material. It is exciting because of some of these key attributes, that some of them are advantages over the other materials that are available now. Specifically with multi-jet fusion, we mentioned that we've got the TPU materials, one from Lubrizol and one from BASF, and both those materials are a little harder than the HP 3D high reusability TPA or the 3D Elastoprint. And so it's a little softer, which is important to note because a lot of times folks want soft materials in elastomer. It's still on the high range, 90A is still hard, so it's not going to be great for 40 durometer, 50 durometer keypads and some of those kinds of parts, but it's great for bumpers and helmets. And through design, you can actually get the softness of the material to come down, i.e. adding lattices instead of building parts solid and so on. So the durometer is a bit of a new idea. It's what we're looking for is cushion. Think about it as cushion. So let's kind of go through some of the other key attributes. Very low fatigue. And what that means is that as you flex the material over and over and over again, it is not going to, it's not going to break down. Kristen, would you mind switching to my screen so I can show some parts? Great, thank you. So I have some parts here that I'm holding. I have a shirt that hopefully you can kind of see. This is a lattice. And I've got another shaped lattice. And fatigue means I can crush these parts and they snap back, and I can do it over and over and over. I can just say they're like little stress balls and they don't break apart. If we did this in any of the other materials that we've done before, like of course there's some elastomer materials that are available in the photopolymer, i.e. carbon, and also Objet, that if you did this, they wouldn't snap back nearly as fast, nor would they be able to withstand doing it lots and lots and lots of times. So if you're looking at things like footwear, if you're looking at straps, if you're looking at anything that's kind of wearable, this material is usable for that. It also stretches. So let's go back, Kristen, if you wouldn't mind, back to the, there we go. Thank you very much. Isotropic mechanical strength, the first bullet down there, it performs very similarly in the X and Y as it does the Z. So if you're stretching something for, say, a wearable, it will stretch extremely well. Isotropic properties, whether it's built in the Z or the X and Y, it's going to stretch nicely. So low fatigue, great isotropic mechanical strength, high energy return, so it's going to snap back, and if you elongate it, if you stretch it, versus if you compact it and then expect it to pop back, it's going to have high energy return. So it's going to perform like a rubber material, like a rubbery type material that's in production, like you'd expect. High tear strength. So if you take it and try to tear it, or the use of the part is going to potentially tear the part, this is going to resist that. So again, for shoe soles, you've got helmet parts, if you're doing something like seating or armrest, anything like that, it's going to resist tear just like a production elastomer, because it is a production elastomer. It's also highly chemically resistant because, again, I mentioned it's PA12 based. Its basic chemistry is based on nylon. It's just got a polyether little molecule stuck in the end there, so it will still resist chemicals nicely. And then very importantly is high abrasion resistance. I mentioned footwear and so on. Like, you can take this material and rub it against concrete, rub it against other parts in your assembly and so on, and it will resist that abrasion very, very well. So that's exciting. So you look at those initial key attributes, and we studied it carefully. We looked at the other materials. As I mentioned earlier, we do cast urethane. Somebody comes to us and says, hey, I've got a bunch of rigid parts in my bill of materials, and then I have some elastomeric components and some sheet metal parts. We can do all of those, but the elastomers, we kind of have this problem of, well, I can make you something that's cosmetic, but if you're going to take it and say run it, have some chemicals exposed to it, or it's going to be high heat or low heat, the cast urethane isn't going to really work very well. So we often ended up in kind of this tricky spot, and now we have an answer. This is going to work beautifully for those sorts of applications. So that's a really, really exciting and big change. Then you look at the other properties here. Let's talk about the next one that we talked about, isotropic. So let's go to the next one, light molecular weight. The parts are actually physically light because the molecule that makes up the elastomer is lightweight. So you can expect as you build it, it's going to make lightweight parts. So they're great for something that has high rotate or low rotational weight, or you're doing something like a machine that wants to start and stop quickly. It works really well for that. You've got footwear that you want to make lightweight. Especially if you add latticing, you can make parts that are extremely light. So that's exciting. Then high performance and wide range of temperatures from hot to cold. So several of the questions here were, how does it perform when it gets cold? It performs very, very well. It's a production elastomer. It's made by Evonik, very similar to their injection molding materials. It's just formulated to be able to be powdered to run in the MJF machine. So if you're, say, making athletic equipment that is going to say be used in snow, you're making ski boot bindings or anything like that, it'll perform very well in cold. Also, anything that you're using industrial, it gets exposed to cold temperatures, it's gonna work really very well, better than any of the other materials that are out there. And then it goes all the way to hot. So we just did what's called the Vicat softening temperature, and that means that you take a sample of the material, you take a blunt ended instrument, put pressure against it, heat it up, and then when it sinks into the surface of the material a certain amount, then you record that as the softening temperature. And the softening temperature is all just over boiling, depending on whether we smooth it or not. So it's about 105 to 110 degrees Celsius. So if you're using these parts in underhood, like if you're using them for, say, HVAC ducting in automotive, using them for airflow in appliances, things like that, you can count on this material living through that exposure to heat. 3D printing is exciting. Being able to 3D print a production grade elastomer is exciting because you can do things like lattices, tubes, bellows, which are parts that have undercuts, like little, fortunately I don't have that bellows. Oh yeah, right here. So this is a bellows. Hopefully you can see it pretty well. It's hollow, and then the inside has this same shape. This is an example of just a basic little part that has been very difficult for us to prototype in the past, because the undercuts inside of this part mean that it's not really castable in urethane. We can't get the supports out if we tried to print it in the TPU and FDM. Like, you can't get in there very well, even with water soluble, and make sure all the supports are out of there. But because this is powder based, we can essentially shake it out of there, and it all comes out. And then this part has been black dyed and then vapor smooth, and it looks like production. And then I can take it and it performs like a production elastomer. It's amazing. It's really, really awesome. And it feels great. It feels tacky, like you would expect an elastomer part, like a production rubber part to feel. So good example of a part there. Something else I just talked about, tubes and bellows. This is another example of a part. Again, this one is, let me show both. This part is just out of the printer and been tumbled. So you see it's kind of a matte, even gray color. This part we then black dyed and then vapor smoothed. And you see that it looks like a production grade part. And then I can take it and flex it like you would expect a production grade rubber one. This is a good example of a part that we originally printed in the TPU material, which is harder durometer. The customer couldn't use the part because this fits over male lure fittings and it wouldn't stretch enough. Also, they have to stretch it or bend it during assembly and then pop it back out and fit it because there's other components all around here. And it was just too rigid in the other materials. So we tried it in the TPA material and it worked beautifully, and they've got it, they're running it, and this is under the hood. So this is an automotive application. While the camera's on here, I just want to go through some other sample parts, just to kind of get your mind thinking about what this material might be able to do for you. This is a prosthetic boot part. This is interesting because it's thin walled. It's about a millimeter, and you see that the shape looks excellent. It comes out great, and then it's elastomer. I can take it and bend it around like you would expect kind of any production elastomer part. Whereas otherwise we'd have to cast this. We'd have to make a rigid master pattern, silicone rubber tool, and then cast it, and probably have some issues with the thin wall. If we tried to do this in FDM, it would be very striped. It would take forever to build. It wouldn't really be very strong, and the materials wouldn't be great. Also, TPU materials wouldn't necessarily be able to flex in the same way. So good example of a part here. Here's another orthotic part. Footwear, custom scanned footbed, and then 3D printed in elastomer that you can bend over and over again. So, and then this can be exposed to high temperature. It can certainly be exposed to the moisture that's going to be in a footbed, and you can know that it's going to live. I can give this to a client, have them take it away and use it, and know that it's not going to, like, well, I know that's going to break down like cast urethane might. Here's another example of a part that is textured on the exterior. So that's something to keep in mind, that you can design in texture and then print the part with texture in it. And then that's an animal grain, like a leather grain. And then this is geometric texture. And this is all elastomer. So this is all printed in TPU, same material, excuse me, TPA that I've been showing, and you can flex it. So it performs like a lot of the elastomer production grade materials, and then you can apply things like texture to it and do it in shapes and areas that you wouldn't be able to otherwise in traditional manufacturing.
Hey, Jesse, we got a few questions here, I think.
Let's go.
First question is, just to confirm, the lattice that you crushed earlier on, can that be crushed in multiple directions with the same flexibility with outgoing plastic?
Yes, I think maybe he or she is referring to this one. I'll actually show several different shapes to answer that. The answer is yes. So this part is cubic, and I'm just going to randomly grab a side and crush it, and then take it and do the 90 degrees, and it does the same. I'll even take it at an angle here, the diagonal, and crush it. I'll just crush it in my hand, and then it pops right back. Then we've got different lattice shapes. So this one, hopefully you can see it decently, is kind of round shaped. And the cool thing about this, you have the idea of being able to tune lattices. So this one doesn't crush in the same way, same material, but just different shape. It actually resists crushing, and then it pops down, pop like down. And so you can get kind of a different effect out of the lattice, even though this is the exact same material. Just some design can really impact the way that it crushes. So if you're making footwear, you could tune the lattice to be able to, say, be more rigid in the center where the weight of the person is, and then lighter in the outside to get different performance. This one is kind of a diamond shaped, and it will crush again and pop right back. Can
you do clear parts using a 3D Elastoprint?
We cannot. It is currently the same color as the PA12, so it's gray color. So we can do gray or dyed black are the color options right now. So it's kind of like the early days of Ford. You can get any color as long as it's black. We are working on other colors, being able to say paint, but none of them will be clear yet. None of the multi-jet fusion materials are clear to this point. So that's why we still have SLA in our arsenal.
Can it be handled being glued?
Yes, great question. So I don't have any parts that have been bonded, but we've recently experimented with that, an adhesive 3M that will bond the parts together, and they're as strong as the basic material around the parts. So yes, adhesive works very well on these. So that would come into play primarily if you're going to be building parts that are larger than the build platform, which in Multi-Jet Fusion is about 15 inches by 11 inches by 15 inches cubed. So 15 by 11 by 15 inches tall. So you kind of picture that. So anything that's bigger than that, we would build in sections and then fabricate together. Also, sometimes you might have an assembly that say you want to put something in and then flex around it and glue, or you might want to glue on, like I showed this part, you might want to glue like fabric or leather, or say if you're going to be doing a wearable, you might want to glue something to, and yes, you can glue to it and it bonds quite well.
But we cannot do you can't print multi-materials. There's a couple questions on that.
Yes, good question.
You could print on top of another part.
That's right. You cannot at this point, like if you printed one part in rigid and then take it and set in the build and then print on it, we can't do that with this technology currently. However, I would say that something that is to consider is that you can 3D print in different densities, so by your design. So if you have, a lot of times we do multiple materials because you can't make a rigid member in the part. You need to say, put in a piece of metal or a thicker piece of plastic and then mold rubber or plastic around it. And with Multi-Jet Fusion, you could make that, you could print in that solid, design it in your part, that solid center part. Like I'll show this again, has got this little label here where it's solid and then lattice underneath. So this is going to perform differently than the lattice underneath it. So the reasons for overmolding and multiple material molding might be different when you can 3D print something with a solid beam in the center and then lattice around it to get different compression. Hopefully that might answer that. And again, kind of get the wheels thinking about how you might use this. We can also help with that, of course. We can help with the design for, say, latticing and figuring out different compression rates. So then, are there other?
So,
Kristen, you've gone mute. There we
sorry.
go. Oh, that's all right.
So we are nearing the end, but we can go over if people want to stick around. Jesse?
Sure. Yeah. I mean, if there are still questions, I'd be happy to go through them.
We still have the resource reference designs as well.
Yes, yeah, I was going to go into that. We've got some more slides here, so let's look at those. So we just have some reference designs here, meaning examples of how you might use this material or how our clients have used it. So I mentioned ducting and bellows. This is important. The reason that we show this first off is because this has been very, very difficult to prototype in production materials in the past. So we often end up with a compromise, or you have to kind of say print it maybe in something rigid and then go straight to tooling before you can actually get an elastomer that you can use, either that you can expose to the temperature or the chemicals or the extreme strain that you have to use to get it onto the assembly and so on. Now you can 3D print it in production material that's capable of doing all that, and we can get you prints in a week or less. You can change designs. You could try printing multiple designs at one time to try several different design ideas and get them back in a week or so with no tooling. So it's amazingly capable of producing, we talk specifically about ducting and bellows. Then think about this, not just for ducting and bellows, but other applications that might be hollow, maybe go around a corner, maybe have some features inside of them. So things like airflow dams, things that are gonna affect how fluid might go on a production assembly line, those sorts of things. There's so many applications that can be used. So then some of the advantages here, high chemical resistance, it's soft, so it can do that flexing, high tear strength. So if you have to stretch it around something to fit, it will work. And then exceptional fatigue resistance. You need to take it off every single time. You can do that lots and lots of times. So really exciting there. Just reference design idea. The next one.
I wanted to real quick, Jesse, just make a note for those of you that have to drop off. This webinar will be available on demand on GoProto's website within about 24 hours. It'll be this and all of the previous webinars are on the resources page at goproto.com/resources.
Thanks, Chris. And also, I will kind of note, there are so many materials that we're talking about here that we've really very just briefly touched on a lot of them. So you need more information, you want to talk about it, maybe get a sample part, maybe a spec sheet. Our website's a great resource. And of course, we are as well. You can also, we've got local business development managers in regions around the country, in the US. And then you can always get a hold of us and we'll help answer your questions. Okay, so with that, then just a couple more minutes here. Let's just talk through the next reference design after this. So we talked about sportswear. This part is a footwear part that we designed. You can hopefully see my little piece. This has got a hexagonal shape inside the part here, flat place where someone's heel would go, and then the sole, and the sole has got an undercut that runs all the way here. Wouldn't be able to be manufactured really any way other than 3D printing. And then you can tune, this is quite rigid. So if you had a 180-pound person standing on it, it wouldn't just fall apart. It's quite rigid in the middle, but it's then compresses on the outside. So if your heel, if you're kind of, pushing on it, it's gonna flex. So we just wanted to show this as an, oh yeah, you can see it really quite, I saw it there for a second, the undercuts. Can't get, oh, there we go. I guess it's just kind of in profile. You can see there, those undercuts are things that would be extremely difficult, very, very expensive, if even possible, to make in an injection mold tool. So you might be able to 3D print some parts that you can't make any other way. So if you wanted low volume, but production capable, this might be your actual production material, production process. Okay, so then back to the screen.
Quick question. How long does it take to print the sportswear example?
Yeah, great question. This would print overnight. The prints in Multi-Jet Fusion range from about, if you have a full build, so I mentioned earlier that it's 15 by 11 by 15 roughly, that full build takes about 18 hours to print. It then needs to cool, and then we take it out and finish it and ship the parts. So the average lead time for Multi-Jet Fusion is usually quoted about 3 to 5 days, and that's about how quickly we'd be able to print that. We can do faster if necessary. Then another reference design here is end of arm tooling, just kind of examples to show you what you might consider doing. This is a part that's got a trapped volume on the inside, or nearly trapped, where you wouldn't be able to get that shape out of an injection mold tool. It wouldn't be able to come out. You'd have to spin or rotationally mold it. And this is something that we can 3D print. 3D printer doesn't care. You've got that hole in the end, so the powder can be removed. And then you've got this incredibly complex shape that you could tune to do exactly what you want in end of arm tooling. So if you need something that's soft that can grab on to something, or maybe you need a certain pressure to say be able to do an assembly properly without crushing it, you're tuning your forces on your robotic equipment. End of arm tooling in 3D printing is extraordinarily powerful, and then when you add this elastomer material, then the world just opens up on things that you can do with those end of arm effectors. Soft 98 durometer, very low fatigue, again, same sorts of things that make it good for the other applications that we showed. Great for here. It's also lightweight, so if you have quick rotational or quick momentum start and stop sorts of things, this material works great for it. And then high abrasion resistance, so it can go through those cycles a lot of times. You have something running by it, a lot high speed, it's going to wear, it's going to resist that wear quite well. Okay, nearly open. Then I guess there are the additional questions. It's kind of the end of the presentation as we have it. If there are any additional questions, I can answer them now.
Let's see. So what is the flammability resistance of the 3D Elastoprint material? For example, auto versus rail versus aerospace standards.
Good question. It at this point is HB rated, horizontal burn, so it is not V0. It does not have the highest flammability rating, so it's not flight rated. It's not flame rated at this point. So just straight up, it needs to be used in applications where flame rating isn't critical. That's one of the things that it can't do yet at this point. They probably will add that. Evonik is a giant material company that is got a lot of very highly trained chemical scientists on it, so they know that's a question that needs to be answered. Same thing back with the PA12 material. Same question. Getting that flame rated is important, and we're working hard on it.
Can you talk to heat deflection temperatures for the various materials with MJF?
Yes. They're all kind of, I mentioned earlier, the Vicat softening, the elastomer materials, heat deflection is a little different in elastomer. And we use Vicat softening, and it's a little bit above boiling. So it's about 110 degrees Celsius. Heat deflection type, Vicat softening. So that's, the answer with elastomers. The PA12 materials are, I think they're about, to something. Kristen, do you have that? Can Can you scroll back quickly to that slide to kind of show where it
Which slide, sorry?
the one that shows the mechanical properties. I think one of them was heat deflection temperature.
No.
Oh, my mistake then.
Yeah.
Yeah, I thought we had it in there. So it's about in the middle of the other materials. So it's similar for PA11 as it is for PA12, as it is for polypropylene is a little bit lower. PA12 I think is 250 or so Fahrenheit, and then the others are a little lower than that.
Okay, well, I think
Right,
that wraps up most of the questions that we can address at this time, but we have Jesse's contact information here. If you have want to follow up with any additional questions. As I mentioned earlier, this webinar, as well as previous webinars and a lot of resource materials will be, are on as well, the resources page on goproto.com. Jesse, do you have any final words?
No, thank you very much for attending. I know this has been a crazy week, and hopefully this is some good diversion talking about materials. We're wide open for talking about more. If you have other additional questions that I mentioned or other parts that you want to quote, we're here and ready to help. Thank you very, very much for attending.